So now we can start at 6:30. First, I would like to introduce myself. My name is Thiago Dutra, and I am with Marek Zglikzinski to share this session, Reciprocating Compressors 1. The first presentation will be done by Jan Tuchovczak, who is a thermodynamic engineer at SECOP in Austria, and his work is liquid slugging in reciprocating compressor. So this presentation is pre-recorded. It will be played now.
Good morning, everyone, and welcome at my presentation, which will be about liquid slugging in a reciprocating compressor. The structure of the presentation will be as following. At the beginning, I would like to introduce the company SECOP, then I will explain what does slugging actually mean. Then we will go through the objects and motivation for the work, simulation methodology, and in the end, I will show the results and conclude the work and propose some next steps. So SECOP was actually founded 60 years ago in Germany, Flensburg, where we have currently our headquarters. Our R&D center is located in Austria, and then we have several other locations in Slovakia, Italy, United States, and China. SECOP is producing hermetic reciprocating compressor for various markets, and our products might be divided in two groups, stationary cooling and mobile cooling. Liquid slugging, what does it actually mean? So during the normal operation of the compressor, we are receiving a vapor or a gas from an evaporator, which goes further to the compression chamber where it is compressed and discharged to the condenser. During the liquid slugging, instead of vapor, we have a liquid coming into the cylinder in uncontrolled manner. The reason for that might be unintentional, which might be, for example, the malfunction of the expansion valve or the high refrigerant charge in the system, or also low load on the heat exchanger or on the evaporator. The intentional source of the liquid refrigerant is the defrosting cycle, where we also open the expansion valve and let the hot refrigerant from the condenser go through the evaporator and melt down the ice formation on the outer surface of the evaporator, which we can see, for example, here. So we are getting to the objectives and motivation of this work. As we know that the defrosting cycle is happening regularly in some systems, then we have regularly the mixture of a liquid and vapor coming through the suction line into the compression chamber. This is something that we would like to analyze, and based on this knowledge, we would like to propose some design changes which would help to decrease the amount of liquid coming into the cylinder, which in a consequence will help us to get the better reliability of compressor and prevent any damage or any faults on the system. Moreover, this topic is also interesting from the simulation point of view, because in the available literature, there is not that much information about this topic. There is only one paper published 2 years ago at IIR Conference, where the scientists or the researchers were performing similar simulation, but they were focused mostly on the inner structure of the suction muffler. How did we actually set up the simulation? So firstly, we took the real compressor that we have in our portfolio. We checked how does the muffler looks like from inside, and we tried to keep the inner structure of it, but simplify the 3D model to only 2 dimensions. This was done because we wanted to save some computational power and time. On top of this basic simulation, I have tried to create some simple geometry modification with the goal to decrease the amount of liquid coming into the muffler. So the case A is in this case the base model. Then we have case B and case C, which has a simple curvature shape, which should help to separate the liquid from the flow. And case D is basically case C with an additional feature here down at, let's say, the separation point, which should also help to decrease the amount of liquid going further to the cylinder. Boundary conditions are shown in this slide. So for the inlet boundary condition, we use the pressure, which is representing the saturated vapor of propane at minus 25 degrees Celsius. For the outlet, I have used the velocity boundary condition. And also, as we have two-dimensional simulation, we have to use the symmetry boundary condition. The duration of the simulation was set to 5 seconds, but the liquid was injected only through the first second of the simulation. As I mentioned before, we were trying to compare two different methods for the simulation. So first one was the volume of fluid, and the second one is dispersed fluid simulation, where we have to set up the mean droplet diameter of the liquid phase, and in this case I set up it to 0.25 millimeters. Here again we have the example how the liquid mass flow through the inlet boundary condition and outlet boundary condition look like. So from 0 to 1 we had 80% of the volume, which is the liquid, and after the first second the liquid phase is set to 0 and we have only gas coming inside. Here, as a consequence, we have the liquid mass flow on the outlet boundary condition. And here we come to the results. Firstly, for the basic design with volume of fluid method. So we see from the beginning how the muffler is filled up with a liquid phase of the refrigerant till the first second. And then right after the first second, the liquid is dragged from the suction muffler towards the outlet. Very quickly, this process lasts like 0.1, 0.2 seconds, and then till the end of the simulation, let's say we have a constant amount of liquid trapped inside the suction muffler. If we take a look on the design with a separation point here, we see from the beginning that there is much less liquid coming into the muffler. But if we take a look here on this separation point, we don't see that it's helping to avoid liquid going further into the suction muffler. The, let's say, duration of the liquid injection is also set to 1 second, and after this second the liquid is escaping very quickly out of the suction muffler, but still we have some amount of liquid trapped inside the domain till the end of the simulation. Here we have the results for the same design for dispersed fluid. So again, the filling up process lasts till the first second, and then very quickly we are actually depleting the liquid from the suction muffler. The important change between the simulation approaches is visible here, that even for the design where we have a separation point, we see that we have a decent amount of liquid coming into the muffler. Nevertheless, the let's say the filling up and depleting process are again very similar. So till the first second we have a lot of liquid coming inside, and after only 0.1, 0.2 seconds almost all of the liquid is gone, and then the decrease of the liquid in the suction muffler is very small. The result that we have seen before, we can see also in these graphs. So here we are looking at the liquid volume fraction in the suction muffler. And as I mentioned, for volume of fluid method, the basic design, we have quite a lot of liquid in the domain. But for the rest of the cases, the amount of liquid is decreased here. For the dispersed fluid simulation, the liquid volume fraction in the suction muffler is very comparable, except the case B. This is actually saying us how much liquid we have in the muffler, but is not saying us much about how effective is the separation of the liquid. This is something that we can see in the following table. So here we have the ratio between the liquid refrigerant escaping through the outlet and liquid refrigerant entering the suction muffler through the inlet, the first line of the table. And the second line is showing the ratio between the liquid escaping through the separation point and the liquid entering the muffler through the inlet. So in case A, we see that 100% of the liquid is going out of the domain through the outlet because we don't have any separation point. Then for case B and case C, we see that the liquid separation efficiency is very low. So still we have most of the liquid going basically towards the cylinder. But in case D, we see some improvement in liquid separation, and let's say 20% of the liquid is separated before entering the suction muffler. Similar results were obtained for another approach for dispersed fluid simulation. Again, case B and case C not showing very good efficiency of separation, but in case D, we were able to reach some significant improvement on liquid separation. So to conclude the presentation here, we have a few points to mention. First of all, we were able to analyze the filling up process and depleting process of a suction muffler by a liquid refrigerant. And based on the results, we were able to say, okay, only one design modification is able to help with the liquid separation in the suction muffler. Both methods, volume of fluid and dispersed fluid, were able to predict the same or similar separation capabilities of proposed designs. And what we found out also is that the transfer of the liquid from the inlet to the outlet is very quick and that the liquid does not retain in the suction muffler. Here are some proposals for further steps in this topic. So it would be really helpful to analyze properly the boundary conditions like droplet size, velocities, pressures, and temperatures. Also, the temperature of the components will play a significant role because it will help to evaporate the refrigerant on the way to the cylinder. And in order to have more precise or accurate conditions, it would be great to apply the pulsating flow condition on the suction. So this will be all from my side. Thank you very much for your attention. And if you have any questions, I will be happy to answer them.
So I think that, okay, so shared now. We have some questions here. Have you done an experimental validation of the results?
Unfortunately, we haven't done any experimental validation so far. We have the test panel ready, but yeah, this would require to use either some visualization method to see what is actually happening in the muffler through some site inside the compressor. Yeah, this is quite complicated, so we don't have anything like that so far, but we have the test bench ready and it's in the plan for the future.
Okay. Thank you, Jan. There is, I think we have time for one more question. What is the average total computational time for one simulation?
Okay, so even though we had a two-dimensional model with a number of cells less than 100,000, the computational time was several hours. So usually the simulation took something between 10 to 12 hours, depending, of course, on the number of processors and the size of the mesh. but this was, let's say, average time of the solution.
I have a question as well that in this same subject. Did you perform any grid independent test on this different size of meshes?
Well, let's say yes. Let's say I started with a very rough mesh, and then I was decreasing the number of cells, but I stopped at some point to not spend a lot of time on computational. So I had one simulation that had, let's say, the double of amount of cells, but then the time was too long, and the results were showing basically the same structure of the flow coming into the muffler.
Okay. Okay, thank you, Jan, for the nice presentation and for this nice work.
Thank you very much as well.
Now we move forward to the next presentation. The next presentation will be carried out by Stefan Gobel. Stefan Gobel is a research associate in the Institute for Energy Efficient Building in the Indoor Climate. And his work is entitled Evaluating Refrigerants Using Dynamic Reciprocating Compressor Model. So it's on you now, Stefan.
So yeah, welcome for your kind introduction and welcome from my side. As already mentioned, I'm from the Institute for Energy Efficient Building and Indoor Climate. And yeah, since we have our own Modelica library in particular for building simulations, we also tried to do models for refrigerant circuits in Modelica. So today I'm going to present a Modelica compressor model for reciprocating compressors. And first of all, I would like to highlight three aspects at the beginning, because first of all, it's a Modelica model, which is quite rare in the field of refrigerant circuits. Secondly, it's a physical one-dimensional white box model. And last but not least, real gas behavior is also considered. So let's start with a look at the need of this work. We all know that through increasingly strict political regulations, we are forced to find new ways, respectively new refrigerants for heat pumps in general. So in this picture, you can see a few alternatives to the reference fluid R410A. That was a work from a colleague of mine, which was published a few weeks ago at the Gustav Lorentzen Conference. So we are forced to get the global warming potential lower than 150 and the ozone depletion potential equal to 0. But nevertheless, high efficiency is should be made. But usually those studies are made with steady state analysis, which are not considered the dynamics. So in our work, we are now added with our new model also data for the dynamic analysis, and this can be shown here. For example, we can take the discharge temperature into account to help doing the oil selection, or the pressures to help doing the construction process. To sum up this motivation, I could say that we try to evaluate refrigerants with respect to dynamics. And for this, a physical compressor model is crucial. Real gas behavior can influence the results, and especially if we have really high outlet temperatures. For example, in the case of carbon dioxide or propane, we are close to the critical point or even above the critical point. And in this area, it's quite complicated to describe the fluid data. So today we are talking about a Modelica compressor model, and let's see how it works. But first of all, I want to make a small comparison with common approaches, in particular in Modelica. Usually in Modelica, you only find empirical approaches, which means that you first of all need a whole map of efficiencies. So typically for the isentropic and the volumetric efficiency to describe the energy flow and the mass flow. Furthermore, you need the thermodynamic state at the inlet. And with this, the black box model can then describe the thermodynamic state at the output. And with these values, you can calculate further data. With our white box approach now, we only need the thermodynamic state at the inlet, of course, and the type of fluid. And then the model only gets the crankshaft movement of the model, of the compressor, and then the model is able to calculate not even the thermodynamic state at the outlet, it calculates the thermodynamic state of the fluid during the whole compression process. And of course, then you can also calculate efficiencies like the isentropic and volumetric ones. So let's have a look how it works in detail. The structure of the model is typical for Modelica in this kind of polymorphic way. That means the whole model consists of several submodels. So to go with you from the left side of the picture to the right, first of all, we have the geometric model, which takes the crankshaft position into account to calculate the actual volume of the compression chamber. And then the compression process model that calculates the thermodynamic state of the fluid during the whole process. It's connected to fluid ports, which represents the mass flow at inlet and outlet. And furthermore, then we have a heat exchange model, a two heat exchange model. The first one calculates the heat exchange from the gas to the chamber wall, and the second one from the chamber wall to the environment to describe the heat loss. And in between the two models is a heat capacity to describe the heat capacity of the compression wall. So this structure helps us because it's universal applicable, and the changes can be made in short time because you only have to change the parameters of the submodels. Because we don't have so much time today, I would like to focus on the compression process because I guess for the most of us it's the most interesting part. The compression process is actually described with only two main equations. On the right side, you can now see the control volume be chosen for the energy and the mass balance. And the energy balance then takes into account the loss energy and the friction work. And usually you can then calculate the enthalpy of the fluid. With the mass balance, you usually get, of course, you get the actual amount of fluid inside the control volume. If you divide this mass through the volume of the chamber, you get the density. And to then calculate the thermodynamic state, you already have two independent state variables. But usually we are using the Helmholtz equation of state. And the Helmholtz equation of state needs, in general, the density and temperature as independent variables. This is not given so far. So usually iterations are made at this point. For example, the RefProp library does so, but these iterations are slow, and so we added for our fluid models further regression functions. For example, functions with input as which are using as input the enthalpy and density to calculate the temperature, and then we have temperature and density and can go in the Helmholtz equation. With this process, we can speed up the simulations. Yeah, and now let's have a look how the results looks like. First of all, the model is now able to calculate time continuous values. That means in this case it's made for carbon dioxide with a quite high inlet temperature, so outlet temperature is really high. Just underline that the model is able also in above the critical point, and also the mass flow is described at inlet and outlet over the time. Furthermore, we did a small parameter study In this case, you can see the isentropic efficiency for 4 different refrigerants over the pressure ratio P. And the same we have, of course, for the volumetric efficiency to describe both mass flow and energy flow. Since it's a physical white box model, we can vary any other parameter. So we also did a few studies to calculate how the compressor speed influence the results, which we can see here. But the model is quite complex and it's not real-time capable. So if we would really use it in annual simulations for buildings, for example, we have to reduce the complexity. This is possible. We find a few correlations to do so. So for example, for the isentropic efficiency, it's quite good possible to use a square function, which can then describe the efficiency with 3 fluid-dependent variables. And in this case, the RMSE is also quite low. For the volumetric efficiency, of course, we use the linear approach, but we also take the molar mass into account. So that the parameter M is not fluid dependent. It's the same for all 4 fluids. In this case, the correlation would be only dependent on 1 fluid dependent value. And also here, the RMSE is quite low. To sum up my work now, we saw that it's also possible to implement physical models in Modelica, in this case for a reciprocating compressor. The model provides reliable data and fluid-dependent values. We also added some correlations for faster simulations that can in future be used for long-time simulations. And the model is not completely validated, but we will do so in future. You can see on the right button corner our new compressor test bench, which will be used to validate it in future. And then we can create further multidimensional maps by very other parameters. And these can then be applied, as I said, in long-time simulations and coupled in a whole heat pump model. So thank you very much for your attention, and I'm happy to answer your questions.
Okay, thank you, Stefan, for your nice presentation. We have no questions so far, this Slido, but I have one question about the model. Did you take into account valve dynamics in your model?
Yes, we did. The valve dynamics are described with the Bernoulli equation, but we have an effective area which is dependent on the fluid. So in this correlation, which I haven't shown here in the presentation, but it's also depending on the molar mass.
Okay. And leakage through the piston cylinder clearance is modeled as well or not?
Yeah, it's also modeled because it's part of the geometric of the geometric submodel.
Can I make one question? Marek speaking. So this simulation is very much related to reciprocating type of compressor, correctly? It's in general for any kind of compressor type we can have.
Yes, thanks for the question. Actually, it's it can work with any other kind of compressors because the geometric submodel only describes how the compression chamber changes over the time. And if you change this geometric model, for example, for rolling piston compressors, it should be also possible. So the general approach should be used, can be used for different part of compressors, different types of compressors.
Okay, now because generally the compressor type are very much linked with refrigerants because of its specific conditions, like for example temperatures. So you are not using certain compression ratio on certain type of machines. So I think this is very general kind of approach, okay, to select refrigerant to be used, for example, in different situation, or to find alternatives with acceptable efficiencies.
Yes, that's true. It's the first easy approach to find different refrigerant, also maybe mixtures, and then you can look more in detail if you think you have find some interesting ones.
Okay, thank you, Stefan, for a nice presentation. Now we have to keep in our schedule. The next presentation will be performed by Matthias Castro. He is a research engineer at SECOP, Austria. And the work he will be presenting for us here is the cylinder deformation sensitivity study using FEA. Matthias.
Thank you, Thiago. This will be also recorded, right? Hi, everyone. Thanks for your time. Thanks for joining this presentation. My name is Matthias da Silva Castro. I work for SECOP Austria, and I'm going to present you our study about the cylinder deformation using sensitivity study using finite element analysis. We will show a short company overview, objectives and motivations of this work, past studies, the methods used, results achieved, and the conclusions. SECOP is a reciprocating refrigeration compressor manufacturer with over 60 years of history. Recently, we opened a new R&D center in Gleisdorf, Austria, and our headquarters are currently in Germany. We provide hermetic reciprocating compressors, controllers, and refrigeration solutions. So the objective of this work is to understand how the cylindricity error is accumulated to manufacturing errors when we talk about the cylinder of the compressor. So how the crankcase is deforming and has some manufacturing mistakes, and how this affects the clearance between the piston and cylinder when the compressor is working. And the approach we decided to use here is a sensitivity analysis to evaluate how those factors are affecting the deformation, what are the most relevant factors, what we can focus the studies if we need to reduce a specific amount, and what is the main contributor. And the motivation is basically the growing request of improved quality and efficiency of hermetic compressors, and to achieve feasible designs in a shorter time, in a more efficient way, in a more automated way. So about some past studies, I was actually presenting some works in the past on the prediction, how to predict the shape errors in a crankcase cylinder. In this case, evaluating the differences of how the threads of the screwing in the head group affect this deformation. So I was modeling it in a different way. So using a normal bonded contact on a smooth and flat surface on the screw, then using some special formulation for they call the ball section method. So in the contact configuration, you can see that it's kind of simulating or representing equivalent threads on the bolt, but the threads are not actually modeled, it's only numerical. And at the end, also using the 3D fully modeled threads, and then evaluate how this was affecting. And we did find that yes, each simplification is having a significant effect on the prediction of the cylindricity errors. And yeah, we also showed here how to calculate those amounts using the results of the finite element model. It's not a standard result from the software, so we need to export the node coordinates and the displacements of the nodes, and then manipulate this data until we can really show the cylindricity values, and taking into account that we need to remove the rigid body motions and consider only what is really the deformation itself. I also did my master work in a similar topic, proposing an automated method to minimize shape errors in a specific region of a part using finite element analysis and topology optimization. So it was an academic study, so not related to compressor, but it can perfectly be related to this, because we are selecting a region of the part which we want to basically preserve its shape, having it very perfectly, in this case, rectangular, and change the structure around it in order to minimize this deformation. So you see how when you increase the objective to preserve the shape of this blue area, the material is distributed in a way that this area here is having really minimum deformation, and then the material is absorbing the deformations and throwing the deformation to other places, basically. Also some work here for fan, for example. They evaluated the friction losses on dynamic simulation models for different given piston profiles and how they interact with the cylinder. So it's basically also taking the deformations of the part and studying how it's affecting the friction losses. IIR also here included the thermal deformation of the cylinder obtained via CFD on the dynamic engine simulation, also predicting the deformations of the piston here and checking how significant it could affect the output results. And also this work from Telsemeyer, the thermal deformation of the piston profile, but here they were interested on the effect on reliability and the fatigue of the piston. We're having some cracks around here, and then studying these deformations here, they could improve the design. And also, study the deformation of the piston and the liner, consider thermal, assembly loads, roughness, and the shape of the piston grooves and how it's affecting the deformations. And finally, the results on the engine design in this specific case. So the method we chose to work here is the finite element model. And for that, we had to include the head group part and the crankcase. And the specific way of modeling some parts, for example, the gasket elements, we have to consider the gasket properties as it should be, considering the closure versus pressure curves, which are nonlinear, the ball pretension elements for the screws, where we have to convert the screw torque using the friction coefficient and screw parameters to define the force, the tension of the screw in newtons, and also the temperature on the parts. And we chose to do the sensitivity analysis to evaluate how different factors are affecting cylindricity values, and at the end being able to join this together with the experimental results, experimental measurements of the cylindricity that is made actually with and without the head group assembly. Because at the end what we have is on the numerical model a perfect cylinder. On the real parts we have manufacturing errors, which the cylinder without any load has already some cylindricity error, and at the end we have the deformation when we measure experimentally together with the manufacturing errors. So we cannot decouple them unless we do some manipulation of the data. The results we get from this numerical model are as I mentioned, we need the node displacement and the node coordinates to calculate the cylindricity. and we can calculate the roundness and cylindricity for each section, and totally the cylindricity after we can remove from this data the rigid body motion of the part. At the end, we have these plots of cylindricity. Here you see that we eliminated the rigid body motion and we have only the deformation. And we can check it individually per sections, and that's useful for comparing with the experimental results at the end, which you can see in this slide. We had a good correlation between the simulation and the experiment. The dotted line here is the measurement. So you see the shapes are corresponding quite well. And here we didn't do any calibration of the friction coefficient on the screws, measurements of the actual tension, and so on. So considering that, it's agreeing quite well. For the sensitivity study, we decided to use the screw torque, the material properties as Young modulus, the gasket pressure curves, and the temperature as factors. And we defined the standard plus minus 20% variation for each factor. And you see here, for example, the effect of the ball pretension and the Young modulus, and the colors are the cylindricity. So you see that the higher the ball pretension, the higher the cylindricity. The higher the Young modulus, the smaller the cylindricity errors in this direction. So yeah, here it's a parallel chart of the variation of the factors. Yeah, because of confidentiality, we are not showing the values, but always in percentage. And here we can see that the most significant factor affecting the cylindricity are the ball pretension and the Young modulus of the crankcase. And yeah, we disregarded the stator stiffness in this case because it was not affecting that much the results for this compressor. And at the end, we have this statistic distribution of the cylindricity. And with this in hand, we have for a given variation of plus minus 20% of each factor, we have a response of changing plus minus 39% only on the deformation talking here. And as the experimental results showed good correlation with the simulation, and knowing the distribution of the machine parts, what we measured experimentally, it's possible to easily add them together now, the deformation part and the numeric part, and we have a total cylindricity distribution of plus minus 41% in this case, noting that, of course, the maximum is different. So it's only the percentage amount we are discussing here. And the benefit of this is that it's measuring the cylindricity on crankcase as it is only the part alone is quite common practice. But if you want to know the final results and make a study to know the final distribution, statistical distribution there, you would need to do a very complex assembly procedure, measuring before and after assembly, special device to measure with the assembled head group and so on. So mixing this numerical and experimental approach is quite beneficial in these regards. That was all. Thanks so much for your attention. And now we can open for some questions.
Okay, Matthias, thank you for your presentation. I think that we have one question. Which factor has the biggest impact on cylindricity, except the manufacturing error?
Well, as we saw there, between those four factors we considered, there is a similar effect on the ball pretension and on the Young modulus, on the material properties from the block. But you have to consider in that case, for example, as you saw from previous works, we didn't go deep on the details how to model the screw threads there. So it could be that this factor is really even more relevant. So that there is this possibility. Yeah.
Okay, thank you. And there is also, I think that we have a time, because this session we have one more class than others. So I think that we can move to the next question, which is what will be the impact of cylindricity on performance?
Well, this is not an easy question to answer. But at the end of the day, we could have two different kinds of effects here. On one side, we are changing the clearance between piston and cylinder, right? So you could have one bad effect, which would be increasing leakage. So for a certain clearance, you would have a distribution around it could facilitate having more leakage or not. And on the other extreme, if you are decreasing the clearance too much, we start having asperity contacts, and that could also influence performance by increasing friction. So we have this main two kind of effect, but it's really an experimental evaluation to see how it will influence.
Okay. Thank you very much, Matthias, for your nice presentation and explanations. I think we can move forward to the next presentation,
Okay.
which will be presented by you as well, right?
One more time, yeah?
Yeah, so, but I have to introduce you again. So this is Matthias Castro. He is a research engineer at SECOP, and now he will present the paper. It's loading on the screen right now. Let's see. The influence of compressor speed fluctuation on bearings design. So Matthias, please go ahead. Thank you.
Hi everyone, thanks for joining this presentation. My name is Matthias Castro and I'm going to present our study from the influence of compressor speed fluctuation on the bearing design. I'm going to show a little bit about our company overview, the objective and the motivation of this work, the methods we used, how we did the modeling using AVL Excite, the simulation workflow, the result achieved, and some conclusions. SECOP is a reciprocating refrigeration compressor manufacturer with over 60 years of history. And recently we opened a new R&D center in Gleisdorf, Austria, and our headquarters are in Germany. We provide hermetic reciprocating compressors, controllers, and also refrigeration solutions. The objective of this work is to evaluate the speed fluctuation influence on the hydrodynamic and asperity power losses, contact pressures, and oil film thickness. So those are outputs from dynamic simulation for the crank train of the compressor. And we are using DOE methods based on finite element and dynamic simulations to be able to make those correlations. And the motivation of this work is that the speed fluctuations can occur basically when we have high loads in conjunction with low inertia rotating parts in a compressor. And by lowering the asperity contact pressures in a bearing, normally that will improve reliability. And having a precise numerical model, which includes all the significant phenomena that are present there, allow to optimize compressors in a more assertive way and in a shorter time. We use the combination of numerical models in this work, starting off a 1D numerical model on GT Suite, which has all the valve behavior and the compressor thermodynamics and the rigid body dynamics. And this is a very fast solving model, which allows us to run a lot of simulations, but it's not so precise as the others. Later on, we have a 3D finite element model using AVL Excite. And here we have all the flexible body dynamics, EHD bearings, fluid dynamics. And there we also have two different levels, a full model and a simplified model I'm showing later. And then we use DOE, design of experiments, to correlate the factors we are changing to the output parameters. And then we do the post-processing also using AVL Design Explorer, and we can have the sensitivity analysis there. As I said, in the AVL model, we have two different sizes of models. So we have a full model, which includes all the parts, all 6 flexible bodies in this case, 5 EHD radial bearings, and 1 nonlinear axial bearing. And here we do a preliminary study. When we can identify which is the critical case we want to dig deep on the details, we define the reduced model, which still has 5 flexible bodies, but only 1 EHD bearing in comparison to the other one. And here we can gain time on solution time. Here we can see what are the bearings we use in the full model and the reduced model. So basically, you will see later, the upper bearing was the chosen one to study deeper. And here we show the simulation workflow, which basically we start in the GT Suite model with the input parameters, including the conditions, the evaporating and condensing temperatures, and the compressor average speed. This model will give us as an output the cylinder pressure and the speed fluctuation for each of the conditions we simulated here. Based on this, we can choose some of the conditions to go to AVL Excite model. And there we have to do the pre-processing with the ANSYS for the finite element models. And we have other input parameters like the oil temperature, bearing clearance, bearing width, rotor inertia. And then we can check our output parameters, which are oil film thickness, asperity, contact pressure, power losses, and so on. And we want to see also what is the effect on those parameters based on the speed fluctuation and asperity contact pressure using the sensitivity analysis. The results from the first model shows us in which conditions we have the highest speed fluctuation. So basically this envelope here is showing us that on higher evaporating temperatures and higher condensing temperatures, we have the highest speed fluctuations. And inside some selected conditions we simulated in AVL Excite, we define what is from those here which has a high fluctuation and speed, which conditions are also critical for the bearing. So which bearing is the most critical one, and we saw that the upper bearing is the most critical one. In this slide, we can see that increasing the rotor inertia decreases speed fluctuation, as this is the blue line, and operation condition becomes less critical. We also evaluated the effect of the speed fluctuation on the asperity pressure. Based on the reduced model in AVL Excite, considering only the upper bearing of the compressor, we saw that the fluctuating speed increased the asperity contact pressure, and fluctuating speed also increased the total pressure in the bearing. To do that, we consider one reference case running with constant speed and another case with fluctuating speed. So you have a bigger contrast between them. In black, we have the constant speed. So you see that the contact pressures total and asperity are lower than the red curves. And in both cases, we also see here on the 2D pressure plots, the asperity contact here on the edge of the bearing. Here is a zoomed in area of this small area here. So this is the upper edge of the bearing. You see how the magnitude of the contact asperity pressures are higher here where we have the fluctuating speed. For the sensitivity analysis, we chose 5 parameters, and we are changing them basically in a range of 40%, most of the cases plus minus 20%. And we did that to vary the same amount on each parameter and see which one is the most contributing to the asperity pressure, for example, that when we have speed fluctuation on the compressor. Again, based on the reduced model for AVL Excite, and the most critical factor showed to be the bearing width, and the second most critical was the bearing clearance. And you can see here on these 2D plots as well that in the color scale is the asperity contact pressure, and here we see the upper bearing width, for example, and then the compressor speed, in this case, going up. So of course, with lower speed, lower average speed, we also have higher instant speed fluctuation, and the lower the bearing width, the most critical higher the disparity contact pressure, which was expected, of course. And the same happens here. Going up on the upper bearing, we have lower disparity pressures, but then going higher on clearance, we have also higher disparity pressures. So concluding, the target of this paper was to evaluate the influence of speed fluctuation on the compressor reliability, in other words, checking the hydrodynamic disparity contact pressures in EHD bearings. And we saw that the modeling using AVLXI is perfectly capable of getting this influence. So we see a significant difference when we ignore speed fluctuation using stable speed and when we have the speed fluctuation there. And we also could evaluate that the model is capable of capturing the effect of higher or lower inertia on the parts on the speed fluctuation. So having the speed fluctuation as a response of the model is also possible there. We could also then later on correlate the speed fluctuation itself to different bearing output parameters that could be correlated to reliability. And the interesting thing here is that you can also use a tool built in Excite with the design of experiment and the whole post-processing here to see what factors are more relevant and the most contributing to reliability, including a model that captures the speed fluctuation as a response of the model. And in that way, we can have a good prediction and being able to refine and optimize the compressors in a more assertive way and having less surprises when going to the experimental approach. And that would conclude our presentation. Thanks for your time, and we are open to questions now.
So thank you, Matthias, for the presentation. Nice work. We have 2 questions at the moment there. The first one is, what is the difference in computational effort between the 2 approaches, that one with the constant speed and the other, the fluctuating speed?
Okay. Actually, here the difference was in the flexible multibody dynamic model. So in AVLXI, right there, we tried with the constant speed and fluctuating speed. And the difference on the models is not so big, not so significant in terms of modeling complexity. But for regarding computational effort and solution time, per cycle, they are also very similar. But for the fluctuating speed case, you need more cycles to achieve convergence. So it's not, the solution is not that different. You could accept similar amount of cycles, but for the paper now, to be precise, we actually run around twice or 3 times the amount of cycles for the constant speed. So it's around 2 to 3 times to be with a good criteria of convergence.
Okay, thank you. The next question is, you see highest speed fluctuations for high gas temperatures. What would be the cause of this?
Okay, so that graph was created using the simpler compressor model, which is less precise regarding the bearing simulation, but is capable to simulate the valves, the mufflers, regarding different conditions of the compressor. And the fluctuation speed is a response. And of course, the speed fluctuation is on one main side a consequence of high loading on the piston, right? So having higher condensing pressures, you have a very high effect on loading. So there is where you have the highest loads. And regarding the evaporating temperature, there is a mixture. It's maybe not so relevant regarding the loads, but it's also influenced the mass flow and so on. So you really need to make this map it's not so linear, let's say, on both sides, on evaporating and condensing temperature, but we have the tools to do that, and that could also be done experimentally. So from there, we only took the information of which conditions we wanted to focus on the study here.
Can I make a question?
Okay. Thank you for your answer.
Thank you.
Yes.
Tiago, question here from my side. Obviously, the inertia of the system is the basic reason of those fluctuations. So you have the variable load, and you have basically torque that is changing. So coupling of those two things are creating the fluctuation of the speed that obviously is creating issues in the bearings because of the speed variation. Okay, do you think that to let me say adapt the torque of the motor, for example, to the required torque to reduce this fluctuation?
I lost your audio for some seconds, so could you please repeat the question?
My question is, do you think there is a methodology or technology to reduce the fluctuation of the speed? For example, now with motors with inverters, is this something possible to reduce the fluctuation, since changing of the inertia is obviously limited in terms of physical possibilities?
Yes, you got exactly the point. So this model we showed here is the simplest way of modeling and the simplest way of driving the crankshaft, let's say. So we consider a constant torque that is in average compensating the loads, and then we have this average speed as desired, but we have this high fluctuation. So you can at the same time have a mixture of a variable torque that is starting to compensate for the fluctuation, and you can even reach ideal case, which if you have a very specific torque curve versus the crank angle, where you would really eliminate all the fluctuation, and that's perfectly possible, and we did it on the software. But then there is the challenge on the electronics and motor side to really be able to make this possible. So to read how the load is coming to the compressor and react on the torque side to minimize the speed fluctuation.
Okay, thank you.
Welcome.
Okay. Well, I think that now we have time for if there is any further question regarding all the works, not only this work that was presented right now by Matthias. And there is a question actually from Konrad Klotche. I think this question was made in the end of presentation of Stefan Gobel, but as we had to follow the time schedule, we had the opportunity to answer the question. So I would like to kindly ask for Stefan to answer this question. The question is regarding the model that was presented by Stefan. Would it be easy to implement multiple work chambers in your model, Stefan?
Yes, thanks for the question. Yeah, the word easy is always a big word. If you are good in Modelica, it should be possible, but it was not focused on this work. So we are not going this way because for us it's only important how the different refrigerants react in the compression chamber and not multiple chambers.
Okay, thank you. I don't know if is there any other question also among you. Also, you can use the microphone to ask if you want. I think for me it's okay. we can, if we don't have any further question, I think we can finish the session.
Close the session, yeah.
Yeah. Yes, and then feel free to move to other sessions that are parallel, going to the virtual lobby. Okay, I appreciate all the audience, and thank you very much for the very nice presentations.
Thank you.
Thank you.
Thank you
Bye.
also from my side.
Thank you as well, guys.
Thank you.
Bye-bye.
Bye bye.
Bye.